Hi guys, I wanted to do a very short video on learning how to partition a segment on the coordinate plane, like the segment here AB, in a particular ratio that's given to us. It's a little bit tricky, so I wanted to start out just with a quick review of slopes. So here we have AB, this segment AB, and just as a quick reminder, the slope is rise over run, and here we have a rise of 2 over a run of 9. So slope tells us how steep or how flat the line is. It also tells us, are you going uphill when walking left to right, or are you going downhill when walking left to right? We can kind of imagine the same sides there, the rise over the run, as sides of a right triangle, and we've been doing this from the beginning of the year, finding the distance or length of a segment. There's the distance formula, which is essentially the Pythagorean theorem. So we can imagine this right triangle, and on the previous page the rise was 2. Here we have a side length, or one of the legs of a right triangle, of 2, and the other leg is 9. So we can find the distance of AB, or the length of AB. I'm going to call it the length of AB. And that length of AB being the hypotenuse squared equals A squared plus B squared. And the length of AB squared equals 2 squared plus 9 squared. And we have 4 plus 81. And if we want to get AB all by itself, we can take the square root of both sides. And we have AB equals the square root of 85. Okay, now the new content. So our task here is to partition a segment. In this case, we're going to partition segment AB. And we're going to partition it by finding the location of point O. Point O is going to be somewhere on this segment, and we want to partition it specifically in a given ratio. In this case, I just chose 3:2, but it could be any ratio. So we know that the triangle proportionality theorem states that if we have a vertical line here, we're going to imagine this right triangle that we've been using. If we find a vertical line and we purposefully make it parallel to the segment over here, then we create some proportional segments. So the first thing I'm going to do is I'm going to make some vertice names. So right now I'm just sketching. I'm just going to imagine point O, and somewhere down here let's call this point P. So we know, as I have drawn here, that if these segments OP and BC are parallel, then by angle, 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 we have two similar triangles. And of course that is because A is congruent to itself, and APO, this angle here, is congruent to ACB, this angle, because of corresponding angles, and likewise this pair as well is corresponding. So by the triangle proportionality theorem, we know that AO is to OB as AP is to PC. So we're going to use this proportion here. It's much more convenient to proportion up a horizontal line, or a vertical line for that matter, than it would be here to find a ratio of a diagonal line like AB. So we're going to try to find the location of this, and by doing so, we're automatically going to partition AB in the same ratio. Okay, so how can we find that location of P and of O? Well, we know that this line segment we could count is 9 units long. And we don't know where this is going to be, so I'm going to assign a variable x, and if this entire segment is 9 units long and AP is x units long, then we know PC is going to be 9 minus x. So I'm going to set up a proportion. I'm going to say if I want a 3:2 ratio, the 3 is corresponding to this segment here, AP, which is x. And the 2 is corresponding to this segment here, 9 minus x. So I'm going to cross multiply, and I end up with 27 minus 3x equals 2x. That's an equal sign. And I'm going to add 3x to both sides, and I get 27 equals 5x. I'm going to divide both sides by 5, and I end up with 5 and 2/5. And just for convenience sake, I'm going to turn that into a decimal, which is 5 and 4/10. So we now know that this length here is going to be 5 and 4/10. So I'm just going to redraw this here now that I know where my location is. I'm going to add back my vertex, and I'm going to count over 5 and 4/10. So I have 1 unit, 2, 3, 4, 5, and 4/10. So we're actually going to be located here at x equals 6 and 4/10. So this is going to be where, this location here is going to be where P is, and of course the x coordinate of O is going to be the same thing. So I'm just going to label that. This is x equals 6.4. Alright, so now we know exactly where our OP, our parallel line, is to BC. And I just need to find the y coordinate of O. I already know x is 6.4, so I just need to know what my y is. Okay, so how can we find that? Well, there's a couple of different ways. One way we know is we can write an equation for this segment AB, or a line equation. So we know a line looks like y equals mx plus b. And we've already known we're continuing to use the same segment. We know the slope is 2/9. Rise. Okay. And I can substitute in either A or B in terms of an ordered pair to solve for the y-intercept. I'm going to choose A, I guess, just for convenience, 1, 1 here. So I'm going to substitute in 1, and 2/9 times 1 is 2/9 plus B. And I'm going to subtract 2/9 from both sides, so I end up with B equals 1 minus 2/9. And if I want to combine those like terms, it's more convenient to represent 1 as 9/9. And I end up with B equals 7/9. So the equation of our line is y equals 2/9 x plus 7/9. For convenience, I'm going to represent 2/9 and 7/9 as decimals. So if you figure that out, that will be y equals 22 hundredths plus 78 hundredths. Okay, and that's approximate because I'm going to have to just round up here my decimals, but it just makes it a little bit easier. So now this segment can be represented by a line y equals 22 hundredths x plus 78 hundredths. Now we know what x is, so I'm going to substitute that in, and y equals 22 hundredths times, and we know our x is 6.4, 6 and 4/10. And if I figure out what that y equals, then I get 2 and 2/10. So I now know that the location of point O is 6 and 4/10 and 2 and 2/10. And that is going to partition AB in a 3:2 ratio. Thanks for listening.